Hello, I'm Antonio Garufi. I'm a postdoc at Osservatorio Astrofisico di Arcetri, and in this talk I will tell you about some of the results we have obtained in the guaranteed time observation of sphere. This is a first collection of images, some of the most impressive ones that we have, but there are many more that I will tell you about. First, some politics of the sphere. Consortium is composed of several European institutes. A lot of researchers are involved. We have had approximately 260 GTO nights in these 5 years, and some of them were dedicated to the survey and characterization of circumstellar disks. Within this survey, we have obtained more or less 60 planet-forming disks imaged. We have 30 publications already out, but many more will be out soon. Most of the images you are used to, that you see from VLT sphere, are obtained in polarized light. That is a very good method to actually trace scattered light from disks, and in particular what you see most of the times are Q-phi maps, so-called Q-phi maps. It's an algebraical trick to obtain the centro-symmetric pattern of the polarization, which is most of the scattered light that we expect from protoplanetary disks that are certainly illuminated by the star. This is an age versus mass diagram of the GTO sample that we have built. You can see that we have a number of big stars that were the first objects to be observed. Some of them were already imaged, were already known before the GTO sphere. Some others have been imaged for the first time. But then we slowly moved to T-Tauri stars that are technically a little bit more challenging because of the relative faintness of the star compared to the Herbig. And here you see a collection of any age and any mass when we are in the T-Tauri stars framework. But then we even decided to really focus on younger and younger objects, in particular on the Taurus forming region, where you can see some of the results we are working on, where probably the disk is not as well illuminated as the previous example. So images are not as fascinating as before, but these are really important results to really put our first images into a broader view of planet formation and evolution. I sometimes plot this near-infrared versus millimeter diagram, which is the brightness we have in the millimeter versus near-infrared. So the millimeter brightness, as you can imagine, is a sort of proxy of the dust mass, whereas the scatter light brightness is somehow telling you how much is the outer disk illuminated by the central star. And this diagram is somehow naturally divided protoplanetary disks into different categories. It's kind of intuitive to understand the low mass and the high mass disks. It's less immediate to understand that the transition disks are those that are very bright in scattered light because they're directly illuminating. There's no inner disk that basically prevents the outer disk from being illuminated. While we have the full disk where the inner disk is basically casting a shadow, a partial shadow, a penumbra on the outer disk, and therefore the disk in scattered light looks relatively faint. So we came up with this sort of classification, broad classification, kind of qualitative classification of protoplanetary disks a couple of years ago, where, well, we may disagree about giant and spirals, but there's certainly some distinction about some disks having spirals, some others having rings, some others looking faint in scattered light, and so on. So the most obvious example is those of transition disks, where we have a cavity clearly imaged in the millimeter and the scattered light. And one of the most interesting results of these years is probably that most of the time the near-infrared cavity size is smaller than the millimeter cavity size. And as far as we understand now, this is actually a good probe of the presence of companions responsible for this cavity. And in principle, that from the difference, from the discrepancy of these two cavity sizes, we may infer the properties of these companions within the cavity. Then we got the rings, are the most common features that we have from ALMA and we have from sphere. When we have rings in ALMA, most of the times we have rings in sphere, but their morphology clearly looks different. In particular, some outer rings visible from ALMA may not be seen in our sphere images because of the relative height, probably, of these rings at different radii in the disk. So this is telling us a lot about the flaring angle, the disk opening angle of these disks. Then we got spirals, one of the most fascinating features that we have. And it's very intriguing in particular that when we have spirals in scattered light, in ALMA, we do not see these spirals, but we see some azimuthal asymmetries, which is somehow morphologically connected, but not quite to spirals. It's almost one-to-one connection. So that is really, really interesting. In principle, even from spirals, we may constrain the properties, the position of planets embedded in the disk. But as you may know, at the moment, we don't have many of these examples here. So at the moment, this remains kind of conceptual, but not quite confirmed yet. Then we got the giant disks, kind of exceptional disks that are super large, with the possible presence of streamers within the cavity and spirals. These are typically associated, or at least in 2 of these 3 cases here, are associated with stellar systems. So they're probably really exceptional disks in terms of dynamics. And then we got faint disks. The faint disks probably did not get as much attention as they deserved, at least for me. Because actually these are most of the disks that we have in the sky. So I think it's really important to really focus on this in order to get some constraints about the planet formation in most disks. And within this category, actually, we have a subclassification, I think, between small disks and shadow disks, which are completely different morphologies, as you can imagine. Small disks are simply those that are smaller than the coronagraphs that we use to mask the star. Shadow disks are those for which maybe, as I told you, the outer disk is not quite illuminated. And it's really intriguing to see that some fantastic example from ALMA may not be detected at all from sphere. So this is telling us a lot about this morphology of these peculiar objects. So the final sketch that we actually created in 2018 involves some of the results of this demographic approach, where we found that spirals are typically associated with intermediate mass star or kind of old stars. We found rings anywhere, more or less, and we found, very importantly, that faint disks are those that are young, or the other way around. The young disks are typically faint in scattered light. And you can also see 2 deserts around faint stars, just technically challenging. And those that are young intermediate mass star, for which we don't have many examples yet. So it's kind of a deserted area in this diagram. And in the bottom diagram, you actually see the different branches of evolution, according to this sketch. In particular, we have the branch of the transition disk, the long-living transition disk. That is what we have constrained the most in scattered light. And so we are significantly biased toward this special object here, and we definitely need to move toward less special disks, maybe faint or small, and characterize them as well. We also have obtained a number of information about the structure of disks. Typical example is to constrain the disk opening angle in this object, since we really trace the surface of the disk in near-infrared scatter light. And we can see here that at the level, the scattering grains that we trace are somehow at smaller height than the polycyclic aromatic hydrocarbons. Maybe we can draw some gas species and find they are actually in between this and the midplane. So this is a kind of new approach that we are trying to address. You can also see that we really obtained a 3D map for some of these disks when we have the back side of the disk detected, as in this example here. We have also obtained some information, not much, I would say, about the dust properties. through the scattering phase function. That is basically how many photons we have scattered per angle. And that is very complicated in protoplanetary disks because of the disk geometry. It's not as simple as for debris disk. So there are just a few examples of this from our papers, but it's interesting that from them we basically found that we need typically large grains to explain our observations. Shadows are the other feature that we recurrently see in disks that can tell us a lot about the disk geometry. In fact, our current understanding is that shadows are related to the inner disk, casting indeed a shadow on the outer part. And at the moment, we believe that when we have the narrow shadows, the inner disk is misaligned by 70, 80 degrees, so is significantly misaligned, whereas in the cases of a larger area of shadowing, these are associated with smaller misalignments, around 20 or 30 degrees. And in some cases, we even need more regions diversely misaligned in order to explain our observations. What we found is also that shadows are associated with intermediate mass stars, so this is somehow similar to the results for spirals, and also that are almost always associated to a high near-infrared excess, a large near-infrared excess, which is somehow tracing the material in the very inner regions of this. So somehow we're really reconnecting the structure of the outer disk with the geometry of the inner disk. We have a number of other structures being imaged. I don't have time to tell you about this, but keep in mind that these are very important, in particular when we move to younger objects. And this is what we want to do, to really be able to trace the planet formation in the earlier stages. And filaments and envelope and outflow and jets, they actually come onto the stage when we observe these objects here. And so we need to have a good understanding of them as well. And just to conclude, this is the end somehow of GTO, but it's the beginning of our understanding of protoplanetary disks. There are a number of other surveys that will complement our observation. Particularly see Christian Ginsky talk on the Sphere Destinies program. And what to say, transition disks are very well characterized for sure. There is much work to be done, and we are actually doing to characterize younger disks and less exceptional disks, like faint disks or small disks. So this is the direction we need to take, and we are going to take. With this, I thank you very much for your attention.